example. In this case, I have part of a machine, right? I'm not even sure what part of what type of machine is that, but let's take it as part of a machine. There is this curved semicircle member. It goes from A to B. We have the radius for that. Then this AB member is attached to member BC at point B using a pin. And we have this, well, it's connected to member BCD, which is an L-shaped member, right? This member right here. Attached to that, AB is attached to BCD at point B, which is a pin. And the member BCD also is on a roller, right? This is a roller support, and assume that this is some kind of wall. Then this member BCD is also attached to, I would say, a disk, right, at point D. So this is disk, and the member BCD is attached to this disk at point D, and you can think about that as a pin connection. Remember, we talked about rollers, and we said when we were dismantling the in example we did in last class, or dismantling, we said the connection between a link and a roller or a disk, we can look at it as a simple pin because there is no resistance against rotation. So the only kind of limitation it imposes is it does not let the disk or roller, well, let's not use the word roller, we're using it for reaction support. The disk or pulley does not let that to go in X or Y direction. All right. All right. So let's see what is the problem statement. Problem statement says, so they already asked us to forget about the friction. It says the smooth disk is pinned at D and has a weight of 20 pounds. All right. So we know this disk D is attached. It's pinned. The problem statement also says that it's pinned, and we also know its weight is 20 pounds. It's 20 pounds. Now we are told that neglecting the weights of other stuff that we have in this system, weights of the other members, determine the horizontal and vertical components yes, so point C is just a roller. I'm going to add it to the problem statement. Components of reactions at pin B and roller C. All right. So here we are. We have a frame, a couple of members. And the reason it's a frame, hopefully we can see that we have two members, A, B, and B, C, D, and none of them is just a two-force member. They have multiple forces applied to them. So definitely we have multiple force member. So it can be a truss structure. Let's start with free body diagram of the whole structure and see if we can find the support reactions from there, and whether that's going to help us, the free body diagram for the whole structure. So let me draw that. It's not easy to draw. I'll do my best. This is the semicircle there. This is point A, and this is point B, and then we have this straight line there. We have this right here, and it's connected together right there. There you go. So let's put the forces. This is the free body diagram for the whole structure, right? Free body diagram for entire system, for the entire system. So what are the forces? Remember, we are looking at this, right? I'm isolating, that's not what I was looking for. I'm isolating this. AX and AY, exactly. So we have AX and AY. AX, AY. 20 pounds downward from D. Yes, we have the weight there, so we have to take that into account. 20 pounds. BX and Bell. Do we have support at BX at B? B is not, well, one step at a time. Let's start with B. So B is part of the structure, right? We are not dismantling these two members. So we don't really have to put anything unless there was some kind of support there. B is not connected to any wall. There is no in contact. There is no roller. There is no pin that is support for the structure. So we don't really put anything there. Right? If we had something like this as pin, that would have been a different story. But right now, it's just hanging there pretty much. Right? It's just a connector. So there is an internal interaction between forces at B, between member AB and member BCD. But for free body diagram for the entire system, nothing at B. And yes, we should include CX. Right? CX is, remember, this is the whole structure. Don't get lost. This is the structure that we are looking at right now. Is connected at this point A, and there is a roller there at point C. So definitely we have to take into account that force. Put that as CX. Right? And that's pretty much it. So AX is equal to CX. Yes, AX is equal to CX, and AY is going to be 20 pounds. Exactly. So AX, let's just be more methodological and write the equation. Summation of forces is equal to 0. Summation of forces in X direction is 0. Summation of forces in Y direction is 0. In X direction, we'll get AX minus CX is equal to 0. So AX is equal to CX. In Y direction, well, we get AY minus 20 pounds is equal to 0. So AY is 20 pounds. We still need another equation, right? This is, let's say, equation 1. This is equation 2. Let me save this numbering for later. I might need that. We have two equations, 3 unknowns, right? We know AY now, but we don't know AX and CX. We know the relationship between them, but we don't know exactly what they are. So what do? We have to use the third tool we have in our toolbox when we are dealing with rigid bodies in two-dimensional space, right? That would be the finding moments. Now, which point I have to find a moment about? I guess there are a couple of options here, but because at this point we also know AY. So I can either go with point C or point A, right? If I go with point C, well, I get rid of CX, but then I have to find the moment for both moment AX and AY create about point C. So I have to deal with 3 forces, moments created by 3 forces, moment created by AX, moment created by AY, and a moment created by 20 pounds weight downward. But if I find a moment about point A, right, AX and AY do not create moment about point A, so I'm good. I can just ignore them, or just they're not going to be part of the equation. So there are only 2 forces left, only CX and 20 pounds. So it seems like point A is more optimal in terms of how how much calculations I have to do. So let's just go with A. It's positive in this direction. All right, as I said, AX and AY do not create any moment. So let's go with 20 pounds. 20 pounds time, what is the distance I have to use? What should it be multiplied with? 1.5. Let's see. We have this distance there. All right, 3, exactly. So I guess I can, well, just for the sake of make sure that everyone can see that. This is the line of action for force, this 20 pounds. The distance between that, perpendicular distance, and the point I'm finding the moment about is the radius of the circle, which is 3 feet. So I'm just going to multiply that by 3. And what is the sign for that? It's downward, palm of my hand towards negative. Thank you, Samuel. Yes. Towards point A, try to make a fist. The direction would be clockwise. So I took counterclockwise as positive. This becomes negative. And then we have CX. Let's see. CX multiplied by the distance, perpendicular distance between CX and point A. How much is that? That's, let's see. Looking at this, right, 3.5 exactly. So this, if this is the line of action for CX, perpendicular distance from the line of action to point A, right, that would be the distance we're looking for. It's 3.5, right, 3.5 feet. So I'll put it here, 3.5, and would be positive. This is CX, palm of my hand towards the point I'm finding the moment about. Make a fist or go for a fist, and then the 4 fingers show the direction. And this is counterclockwise, so it's positive. Is equal to 0. So from there, we should be able to get CX. And CX would be, I have to look at my notes, 17.14 pounds. Once we know CX, right, pretty straightforward. From there we can, so this is AY, this is CX, and then, so AX is also the same. AX and CX are equal, right? So AX also going to be 17.14 pounds. There you go. So we found all the support reactions, right? 1 at C and 2 at A, AX and AY and CX. All right. Now, what were we asked to do? We were asked to determine the horizontal and vertical components of reactions, which we did. Well, reactions at point B and roller C. We found the reaction at point C, roller. But at point at pin B, well, we have to actually, it's an internal force. So we have to, maybe problem statement is not really worded in a very good way, the way it says reaction at pin B, but it would have been probably better to say internal force at B. But let's just find whatever we can find in this problem. All right. Now we have the reaction forces. Let's take a look at the free body diagram for each member. All right. I just put the goal as let's find all the possible unknowns in this problem and see, at least we can learn more from it. Okay, let's go for member AB. Let me draw the free body diagram for member AB. So member AB. I'm going to try and draw the free body diagram here. Let's do AB. Whoops. Not exactly what I was looking for. Let's draw it this way. This is A. I can't write on that corner. This is B. Yeah, that's pretty bad, AB. All right, we know the force is on this corner. Let me try and move it a little further. I don't have really access to that corner. There you go. I'll draw it here. This is A, and this is B. All right, see what we have there. We have downward force at 20 pounds. We already found AY. We know there is AY and AX there, and we know their values. AY is 20 pounds, and AX is 17.14 pounds. And we're looking at B, that's a pin connection. So we have to take into account when we dismantle or take AB out, right? We're looking at this. Let me clean up figure here, and let's see if we can just draw it there so everybody follows. Right, here is what I'm trying to achieve right there. I'm isolating AB. Right. So the force, the weight of the disk is applied to it. I have two reaction forces at A, and then I'm looking at point B. It's a connection between AB and BCD. I'm gonna have two forces there. Right. And I'll just go based on what I see. Most probably BX should be in this way to keep this in equilibrium, and let's put BY in this direction. I don't know the direction of BY, but I'm just guessing that. But BX, we can pretty see that you need a force in the X direction to cancel AX. Assume BX is equal to AX and BY is equal to 0. Let's see what we get out of that. Maybe that actually might be the right assumption. But let's just do the math because, oh, I made a mistake somewhere. Right, this is not 20 pounds. Why did I make the assumption? Somebody should have told me that. This is the contact between member AB and disk D. Right, so I don't know what that is. Let's just call this ND. I actually don't know. Let's draw the free body diagram for, I can put it here, member or disk D. Free body diagram for disk D. Disk D. If I draw that, well, let's say this is our disk. What we have there? We have one force down, which is its weight, 20 pounds. We have the reaction or smooth contact, ND. And what else do we have there? We have this pin there, right? We have, well, wait, don't get lost. I'm isolating disk D here. All right, this disk there. We have the force in this direction, right? We keep in mind that if you look at disk D and the connections it has with the rest of the frame, disk D is connected to BCD at pin D. Exactly. So we have two forces there. This is a pin. I got point D. Well, let's not jump into conclusion. Let's take a look at the free body diagram of disk D. I should have drawn that first. So 20 pounds downward. A reaction coming from, because of a smooth contact, there is between AB and disk D, so ND. Now we have this pin here, pin D. Now this pin D, if I take the disk out, if I want to compensate for that, remember we said whenever we have a roller or let's say disk or a pulley attached to a member, whenever we isolate that, we have to take into account two forces at that pin, because that pin is stopping this disk from moving either direction, X or Y, or any angled direction. So I have to take that into account. So here goes what I need to do there. I'm going to draw it with a different color. Let's say this is called dx, and call this y I don't know if to put it downward or upward. Let's just put it downward, dy. I'm going to pause here. Is there any question about this one? Did everyone follow what I did right there with that disk? But I'm trying to tell you that that ND that we're going to put on member AB is not exactly 20 pounds because we don't know what dy is. All right, give you some few moments. Look at this. So I draw the free body diagram for member AB. All right, pretty straightforward with AX and AY, and BX and BY because there's a pin there. We got to a point that member AB was in contact with disk D. There is a reaction. There is a smooth contact. These two are in contact, so there is some force between them. I called it ND, and we said, well, why not just put 20 pounds? We'll look at disk D. If you look at disk D, ND, well, it's the, should be the same force applying from member AB to disk D, but in opposite direction. So I put it on that. 20 pounds is the weight. And now disk D also is is attached to member BCD at pin D. Pin D, since it's a pin, there are two forces, there are two members, there are two components of the force, one in X and one in Y. So looking at that, we see that ND is not equal to 20 pounds. ND is equal to 20 pounds if I got the right direction for dy plus dy. Right? And I cannot find it from that three-way diagram because I can write equations in one thing I can figure out is dx is 0 there though, right? Because there is no x component. But dy, I cannot find it from there. All right. So going back to member AB, I have to separate things a little bit here. Let's do it this way. And this, so I can efficiently use the space. All right. So member AB, summation of forces. Now you see that it's not as straightforward as we thought. Right? Because we have two members in y direction we don't know. Bx, oh, it's pretty straightforward, right? Because there are only two members in x direction. Let me write the equation. Summation of forces is equal to 0. Right? Summation of forces in x direction is equal to 0. Summation of forces in y direction is equal to 0. Take this as positive and this as positive. Forces in x, well, bx and ax, so I would say 17.14 minus bx is equal to 0. In y direction, I will get by minus nd plus 20 is equal to 0. The first one gives me bx, but let's just at the end just put everything together. All right, so two equations, three unknowns, bx, by, nd. Obviously, I have to go for the third equation that I have in my toolbox when I'm dealing with rigid bodies in two-dimensional space. And that would be summation of moments. Which point do you suggest to find the moment about in this case? What is the optimal point? It is point B. Thank you, Elizabeth. Yeah. If I put it at point B, bx and by do not create any moment. Ax does not create any moment because its line of action passes through that. So the only forces left are going to be ay and nd. Right, so let's find it around point B, and this is positive direction. I have AB, which is 20 pounds, times, what is the distance now? Can someone tell me the distance? 6, exactly, right? Then now that's the diameter of this semicircle or half circle. So 20 times 6, and the direction would be negative. Right? Going from upward, finding the moment at point B, so this is negative. And then we have ND. Right? ND is, we don't know the force, the distance is 3. and it's in counterclockwise direction. So it's positive. It's equal to 0. Now we have 3 equations, right? 1, I can do a better one there. 1, 2, and 3. 3 equations, 3 unknowns. Unknowns are bx, by, and d. Well, from the first one, we can find bx. From the third one, we can find nd. And once you know bx and nd, from the second one, we can find by. So let me just put them all together here. Bx becomes 17.14 pounds that we know. By and nd. I'm really stretching the space there. If you do the math, you'll get nd as 40 pounds and by as 20 pounds. Well, that we already. All right. These are what we found there. So let's squeeze right down. There you go. All right. That's pretty much what we wanted. But if we want to go further, now we can actually find even dy and dx on disk D. Right? Because we know bx, by, and nd. If we go to disk, right there, try to keep everything the same page. So summation of forces in y direction is 0 in this case. Right? Upward is positive. I'm doing that for the free body diagram for disk D. nd is positive, so upward. nd minus 20 minus dy is equal to 0. Seems like my dy direction is correct. dy becomes nd is 40 minus 20 is 20 pounds. This becomes dy. We know dy now. And if you write the summation of forces in x direction, you'll get also dx, which is obviously 0. There is no other member in x direction. So I can also put dx is equal to 0 from summation of forces is x equal to 0. Right? That also we can find. All right, yeah, I pretty squeezed everything. Hopefully you guys followed this. So just to recap what we did there quickly. Right? I was given this, so I started from free body diagram for the whole structure. I found the reaction forces, right? Reaction that I had at point A, which is a pin. So I had 2 components there, and C, which is a roller. And I had the weight. Use those, I found reaction forces. Now I looked at member AB. There was a little bit of confusion there. That, well, we found, we knew that there are reactions at A. B is a pin connecting AB to BCD, so I put those components there. When I take that out and dismantle this AB, or take this AB out of the whole frame, I put those there. Now we came to the part that there was a contact between disk D and member AB. I went to disk D. Well, that's the general procedure I should have followed. The weight is 20 pounds. And the contact, whatever it is, that force is the same, but the direction is flipped, right? If you're looking at disk D, we should have the same magnitude of ND, but in the opposite direction. So I put it there, and we said disk D, when I isolated that, is supported to member BCD at pin D. It's a pin, well, as we said, it restrains or restricts the motion in X and Y direction, so I have to compensate for those on my free body diagram. I put dx and dy. Looking at that, I cannot find dy from there. Dx is obviously 0 from the beginning. We could see that. So going back to member AB, I have ND there. I use that free body diagram to find ND, BX, and BY, and then use that ND, came back to disk D and found dy. A little bit of going back and forth, but just to avoid the confusion about the smooth contact we have between these two is not equal to the weight of the disk, because disk is not, if the disk was just sitting there, right? If we had some situation like this, if we had the member and the disk was just sitting there, that would have been correct to just put the weight there. But since disk itself has some connection, to the rest of the structure, we have to take into account the forces because of that connection.